We said we want to look a little more at the flame structure, and the way we do this is we use this so-called flamelet transformation. And what it does is we saw that mixture fraction is a really important parameter. In fact, if the chemistry is infinitely fast, we saw that mixture fraction describes the whole flame structure. It tells you, we had this Burke-Schumann model which tells you, what is the temperature and the composition just as a function of mixture fraction. And so we do the same thing then also for, a situation where the chemistry is not infinitely fast, but it's still relatively fast, okay? So, and that's how we do this. We start out here with the governing equations. We assume here unity Lewis number just because it's much simpler. If we don't assume this, we could do the same thing, but the equations will be much, much longer. And so these are the governing equations here: species mass fraction equation, convection, diffusion, chemical source term. Same here for the temperature equation. And then here we have the mixture fraction equation. And the mixture fraction equation, that's the nice thing. It doesn't have a chemical source term, right? Because it's like an equivalence ratio. And so we assume here the low Mach number limit. That's something we have done before. And now we look at the stoichiometric surface. So here we have an example again. This is supposed to be a jet. So we have the fuel come out here. The oxidizer is here. And then, so here's lean, here's rich. And then somewhere in between, there's a surface of stoichiometric mixture. And so we said earlier, if the chemistry is relatively fast, if the chemistry is infinitely fast, all reactions happen exactly at that surface. If the chemistry is relatively fast, then reactions happen very close to that surface. And so in order to analyze this, we introduce a new coordinate system. So x, y, z, that's just a lab scale system, but now we introduce a new coordinate system, x, y, z, that is attached here somehow to the surface. So take the local flame surface or the local surface of stoichiometric mixture and then put an orthogonal coordinate system there. It is x1 then goes in the direction normal to the stoichiometric surface, and x2 and x3, they're in the surface of stoichiometric mixture. And then we replace these coordinates. We introduce a new coordinate system where so I said x1 goes in the direction normal to the surface. That's also the direction in which the gradient of mixture fraction goes, right? And so we replace that x1 coordinate by the mixture fraction itself, because that's the direction in which the gradient goes, which means in which the mixture fraction is changing. The mixture fraction does not change along the surface of stoichiometric mixture, so it doesn't change in the other directions. So we introduce a new coordinate system where we say x1 is replaced by mixture fraction, x2 and x3 are replaced by new coordinates, but these new coordinates, they should be just the same as the old ones. And then the time is replaced by a new time, but the new time also is just replaced. It's just the same as the old one. So the new coordinate system points in the same directions as the old one, only that it's scaled, okay? So the x1 coordinate is replaced by z, which means it's scaled in that direction. So then we can write this transformation. We can do a coordinate transformation. Here, this, let's say psi, that's the, let's say the temperature here is a function of this, and we transform it into this, where mixture fraction here is a function of space in general. So that gives us then the transformation rules. D by dt is then d by dz, dz by dt, dt by dz2, dz2 by dt, and so on, d3, and then here also dt by d tau by dt. And then z2 is basically the same as x2, but x2 is not, x2 is an independent coordinate. It's not a function of time. This is why this is 0. This is the same thing. Here, tau and t, they have the same scaling. They have the same units. And so that's why this here is equal to 1. I mean, this term is equal to 1, and then this one also remains, okay? So we keep these two terms. D by dt is d by d tau plus dt by dz, dz dt, okay? So that's what this is. And then dt by dx1 is the same thing, you know, I mean, you have to replace the x1 now by all the other 3 coordinates, but because they're all independent here, all these 3 go away, and we can do the same thing here with x2. Then also they all go away, except for here dz2 by dx2, because x2 is the same as z2, or z2 is the same as x2. This here is also equal to 1, so here also this one remains, and we get these 2 terms. So then we can introduce this coordinate transformation into the governing equations, in the temperature equation, and this is what we get. So you get some terms, you get the term here with tau, that's the new time, and then we get this term here with here this gradient squared and d2 temperature by dz squared, and then you get all of these which have a d by dz, and then, you know, a d by d mixture fraction, and then also some dependency on z2 and z3. And now we do I mean, that was just a formal coordinate transformation, but now comes the trick that leads then to the flammability equations. We say, if you look at this here, this is actually DNS of non-premixed combustion, where in the beginning you have some blobs of fuel and you have some blobs of air, and then, or let's say you have some blobs of fuel and the rest is air, and then the blue line here is stoichiometric mixture, and then the color is temperature. And then you see here, for example, and you see, by the way, you see here there's a lot of local extinction. Here's stoichiometric, but the temperature is very low. So this DNS was done to enforce local extinction, to try to understand this a little better and so on. Now let's assume we look at regions where you don't have local extinction, for example, this region here, where you see then that if you go in the direction normal to the stoichiometric surface, the temperature changes a lot. Here, the temperature is super high at stoichiometric, and if I go away, just a little bit away from the stoichiometric surface, it's very low. So the gradients in mixture fraction direction, they're very large. But if I look at the gradients in a long stoichiometric mixture, they're very small, right? I mean, there's basically no change if I go along. So the changes along stoichiometric mixture are the changes here in dzj. So they are very small. So everything that has a dzj, we say that's really small, we can neglect it, okay? So then only these 2 terms, the red terms here are left over, where this here, you see, depends here on this gradient squared and on this second derivative. This is the dominating term. It balances here the chemical source term, okay? So these are the leading terms. So it's the diffusion here, you could say, is the diffusion in the mixture fraction direction, and that balances the chemical source term. And then, of course, also unsteady effects, they could be important, but very often they are not considered. Very often we say, you know, that we assume the whole frame structure is in steady state. That leads then to the steady state, steady flamelet formulation. And then these terms are 0, but then here you see, I mean, you could do, first of all, this, we did this for temperature, you can do the same thing here for mass fraction, and then you see it's only this term balances a chemical source term. And this term, here, there was this d times dz by dx squared, and that's what we call here the scalar dissipation rate, okay? We'll see later on when we talk about turbulent combustion, that is the dissipation rate of the, you know, what's called the scalar variance in a turbulent flow. So that's the scalar dissipation rate. Turns out this is the local mixing rate. This is the rate at which molecular mixing takes place. Okay, so you could say, you know, is the rate at which fuel and air mix locally. So if this is high, then they mix very fast. If it's low, they don't mix very fast. And of course, it's related here to the gradients. We said earlier, if the gradients are high, mixing is fast. If gradients are low, then mixing is slow. So that dissipation rate, so this here gives you mass fraction as function of mixture fraction. It doesn't say anything really about physical space, right? That equation, it lost the physical space. The velocities, by the way, they are not included anymore in this equation. So how does the effect of velocity, we said earlier, if you, in a non-premixed flame, if you blow harder, you could extinguish the flame. How does that appear here? Well, what you do really is, if you blow harder, you make the mixture fraction profile more steep. If the mixture fraction profile is more steep, then this scalar dissipation rate will be more steep. Okay, and then you know, this diffusion term here will be stronger, and that in the same way can lead to extinction. Okay, so that's why, so this carries all the effect of the velocity field on the flame structure. It's all captured somehow in the dissipation rate. So the dissipation rate here also, just like the strain rate, is an inverse, has dimensions inverse of time. So here this is diffusion coefficient has units meter squared per second, right? This here has units, z is non-dimensional. This has unit 1 over meter squared, so the whole thing is 1 over second. Okay, so this is an inverse time. And then also this dissipation rate, you can use it, I mean, as a flow time scale, and you can build also a Damköhler number with the with this equation. With this parameter. And here, of course, when the dissipation rate goes to 0, here the dissipation rate goes to 0, you capture the equations here for homogeneous reactor. Meaning there are no gradients anymore. If this is 0, there are no gradients anymore, and then you have a homogeneous reactor. Yeah, this I showed already. This shows the dynamics just, and maybe the only thing that's interesting here is how you get, initially, you get local extinction here in some places, like here, and then later on, this reignites and it keeps burning again. Because, you know, as I said in the beginning, there's a lot of strain, the dissipation rates are high, you get local extinction, but then when mixing proceeds, the gradients get smaller and smaller, and then at some point this reignites again, and that's what we try to understand here with the simulation. This then shows solutions of this flammability equation, and it looks very similar to the solutions of these 1D equations, counterflow equations we looked at earlier. So this here, again, this is a mistake here. This dissipation rate goes up in the other direction, okay? High dissipation rate would be low residence time, and it would give you lower temperature. So this here is low dissipation rate, higher and yet higher. And so shown this temperature as function of mixture fraction. For methane flame, we said stoichiometric is about 0.05, and so that's roughly here. And then, again, this just shows I mean, in a similar way, these flames as function of a physical coordinate, and you see then they are kind of all over the place. This here is heptane, though, propane. And then earlier we saw that if you increase or if you decrease the residence time by increasing strain, or by increasing the scalar dissipation rate, you can get extinction, and that is shown here. Actually, this shows all the possible solution of this flammability equation. You can these are all steady state solutions where just the maximum temperature, or let's look at this here again, we just show the maximum temperature as function of the dissipation rate. And then here you see when the dissipation rate is very small, so this here is shown as 1 over dissipation rate, and then this here means this is very small dissipation rate. Why do we show this as 1 over dissipation rate? Why, you know, who comes up with that? Why not as a function of dissipation rate? Relatively simple, I said earlier. Or I give you 1 more second. I said earlier, with a dissipation rate, you can also form a Damköhler number. And that Damköhler number is basically is 1 over chemical time scale times the dissipation rate, right? Because the dissipation rate is inverse of a flow time scale or residence time. And so this here is like a numerical number, okay? So I would divide this by a chemical time scale, then it is a numerical number. So this, I mean, usually people plot this like this because this is a numerical number. Anyways, this is low dissipation rate. Dissipation rate gets higher, higher, higher. And then at some point you get quenching. And then if you, for even higher dissipation rate, you just get unburned solution, you know, unburned mixing without chemical reactions. But then if I start from here and I go to lower and lower dissipation rate, then at some point I can get ignition, okay? And you see there's a hysteresis here, you know, I mean, the extinction happens at a higher dissipation rate than ignition. And what's interesting also, these equations, they also have solutions here. All of this here is a solution, you know, to these equations, but it turns out the equation solutions to the steady equations, but it turns out they're not stable. They're unstable. You cannot realize these in the lab because they would be unstable. And so, right, so basically what happens here, if you're to the right of this curve, then the chemical source term is larger than the transport term, and you would go up. If you're to the left of this curve, then the transport term is larger than the chemistry, and you go down. And here in this region, it means if I just go a slight little bit to the right, I would go up. If I go a slight little bit to the left, I go down, right? Here, these are stable because I go a slight little bit to the right, I go up, so I stay on the same curve, right? So that's why this is unstable, but we can compute it, okay? And that's sometimes useful. We do this because it allows us also to get this point here a little more accurately. Here's what's really interesting. If you have data and you want to know what's going on with the data. So this shows experimental data from a turbulent flame, and it shows the data as function of mixer fraction. So these are conditional means from the experiment as function of mixer fraction. And now I can look at the equation here, and the equation says d2 wide by dz squared is equal to m dot, which means, so this here shows y as function of z, and this is the second derivative, it's just the curvature of the profiles, right? If the curvature of the profile is proportional to the chemical source term. And in fact, if the curvature is negative with this minus, the chemical source term is positive. If the curvature is positive, the source term is negative. And if the curvature is 0, the chemistry also is 0. There's no chemistry going on. That's what these equations say, right? So that's what we can look at here. So here, for example, here's oxygen. Here, for example, this has positive curvature, which means chemical source term is negative, which means oxygen is consumed here in this region. It's not consumed in this region because there's no curvature here. Chemical source term is 0. And, you know, same here for all these other CO2. All of this here, CO2 is not produced in this region, right? Because the curvature is 0, chemical source term is 0. All the CO2 is produced in this region where the curvature is negative, meaning the chemical source term is positive. Okay? So that's a really good, useful trick to understand. Even if physical space is not the exact same thing, but you can say also roughly, whenever you know you have positive curvature, the source term is negative, you know, it's consumption. If negative curvature is formation, but it's not the same thing. This is rigorous. In physical space, it's not. You can show it like this. Okay, good. So that's just this, and then what's interesting is we don't know what the scalar dissipation rate is, but luckily, you know, I mean, one can also find an analytic solution to the equations that describe here this counterflow diffusion flame. That is shown here. How to, I mean, these are the equations. Now this a similarity solution, similarity coordinate is introduced. Some assumptions are being made, and you can come up with a analytic solution. So this gives you, in this counterflow diffusion flame, let's say, it gives you mixer fraction as function of the, the distance from one of the nozzles. And because the dissipation rate is dz by dy squared, I can also write it as dz by the eta squared. Eta is just a spatial coordinate here. From this, I can determine the dissipation rate, and it comes out to be this. So the dissipation rate is proportional to the strain rate, first of all. That's what we said earlier. I mean, the higher the strain rate, the higher the gradients, the higher the dissipation rate. But, I mean, this shows it's proportional, really. And then secondly, you see it's proportional or depends here on this exponential of an inverse complementary error function. So it's a little bit of complex function, but this is what it is. So this is the dissipation rate as function of mixer fraction, and that's what we often use when we do simulations. I mean, this is just what you would get in a counterflow flame. There are other analytic solutions. We have an analytic solution also that's more fitting for a jet. It also has a little advantage. It gives you, it's described with a much simpler function. It's a log function and not here this complementary error function. But they are, similar and similar shape, and you can use this shape then in a simulation. Okay. So that's what you get from multi-step chemistry, and we can complement that again. I said this in the beginning. We can complement this with what would you get if you would assume, just like the thermal flame theory. What would you get if you assume one-step global reaction? And that is actually a very, very famous paper here by Amable Lignan. He was the first one to describe the structure of methane air flames in the 70s, and he used a one-step model. And this is what you get. I mean, if you show the temperature as function of mixer fraction, you get something like this. This is for, let's say, 0 dissipation rate, and so this would be infinitely fast chemistry. And then if the dissipation rate goes up, then the temperature goes down. That's what we said also. Why is this? Because here in this solution, because the fuel cannot be burned anymore, and the fuel now, or let's look at this one here first. Infinitely fast chemistry, the fuel is consumed at a stoichiometric mixture, but if the dissipation is higher, then the residence time is not as long, then the fuel leaks into the lean region, okay? Fuel leaks into the lean region. That makes a lot of sense, right? But it's wrong, okay? The fuel does not leak into the lean region. If we look at here simulations using detailed chemistry, low dissipation rate, high dissipation rate, temperature goes down, and then low dissipation rate, high dissipation rate. So the dashed line is the high dissipation rate. Here the fuel, and you see the profiles are exactly the same. There's no fuel leaking into the lean region. In fact, what you see here, the oxygen is leaking into the rich region. That's what happens. The fuel is still consumed. What happens with the fuel? It's consumed and forms CO. But the CO is not an H2, but the CO and the H2, they are not consumed anymore. And so the oxygen, because the oxygen is not consumed, it's leaking into the rich region. Okay? So that shows, again, that one-step chemistry is not necessarily right. Okay, so oxygen leakage, that's what you usually have. Here, Seshadri did asymptotic analysis in the late 80s, where he showed the same thing then, using here the 4-step model that we discussed earlier, where you also see that you get oxygen leakage. Now, another thing that's interesting is that people have compared premixed flame with non-premixed flame. They actually have a lot of similarity. In fact, it was Lignan in his paper who said I mean, and you can see why. He said a diffusion flame at the point where you get extinction is like a premixed flame. Why? Because, I mean, in this case, you have the fuel leaking here to the lean side, and here you have a fuel-air mixture. Now, the fuel-air mixture, you know, burns here. I mean, that he said is like a premixed flame, and in fact, you can also observe this in the when you look here at these production rates. So you have, is this discussed here or does this come later? Yeah, so you have an inner layer here where, so here is the fuel. This is rich. This is where the fuel comes into the reaction zone. And then you come here to a point where the fuel is consumed and you form CO, right? That's where you form CO. And then there's a layer here where the CO is consumed and you form CO2. That's just like for the premixed flame. So the argument has been a diffusion flame is very much like a premixed flame where, let's say, the outer structure is the preheat region, and then you have here the reaction zone at stoichiometric, and in the lean region, you see here in the lean region is where really the CO2 is converted to, the CO is converted to CO2. This is why you see this slight curvature here actually in the temperature profile. And so that's kind of like the oxidation layer in the premixed flame. Yeah, so that, I think that all describes the same thing. Okay? So that's what we learned from the asymptotic studies. Any questions? If not, then we come to the, I mean, as I said here, there's a lot of discussion here now on, there's a lot of discussion now here on single droplet combustion, but we're not going to go through this. I think that's the rest of this lecture. And then we go to the next one, and I'm not sure exactly how to do this, but we'll see. This is on the here FlameMaster Flame Calculator. Did anyone download this and install it on their computer? 2, 3, 4. Okay. So 5. I mean, a few of you did. You know, check this out. It's like a video game. It's just much cooler. A lot of things you can do. I mean, in the old days when I wrote this code a long time ago, it worked really well on the Mac because I use a Mac, but I hear a lot of people use Windows computer. It was always very difficult to install. Now, one of my students, Raymond Langer, he actually rewrote all of this. He put it all on with CMake, and so it's very, very easy to install now. I mean, you just type a few commands and it will install. So I want to show you how this code works, what the idea is behind it. I could also do some simulations here and show you actually how it runs. Let's see if we get to this. So FlameMaster is a C++ computer program for 0D combustion and 1D laminar flame calculations, basically a homogeneous reactor. Here premix, non-premix, steady, unsteady, you know, with an emphasis on pre and post processing. You solve these flame equations, a perfectly steered reactor, you know, all these configurations that we use, anything that's 0 and 1D, steady or unsteady, kind of is what we solve. I wrote this with my master thesis, was writing this code, but then, you know, afterwards we used it a lot, we extended it a lot, and also recently we made it maybe a little more usable also. A lot of new functions are coming online. We have a lot of capabilities developed recently, which are not in the public version yet, but they will be probably integrated at some point. For example, relating to more automatic reaction flux analysis, and also related to sensitivity studies, where we do sensitivity studies using adjoint methods. We have published a few papers on this. It's not in the public release yet, but it's something we plan to include, where you can do, with just one simple simulation, you can do a sensitivity study with respect to basically all parameters that appear in the model. And so we did a recent example where I think it's like 100,000 individual parameters. And you can see which one's important and which one's not. So here's how you do this. Go to our website, ITV, you find, you Google my name and you find here the ITV webpage. And then the first thing you do is you go to, you're on the homepage, and there's our LinkedIn link and our Twitter or whatever, and then go like us or whatever you do. I don't do these things, but that's always a good thing. So follow us on to see what's going on in our institute. A lot of fun stuff. And then you go here to the download section, FlameMaster, request login. You need to fill out who you are. We want to know, who's using the code. And then you get a password and you can download it. And then there is a README file. Here, you fill out your name and stuff, where you're from, and then you submit, and then you get a login, and you can install it. These are just some examples. People do experiments in shock tubes, which we then simulate as a homogeneous reactor. So this here shows for octanol is kind of a next generation biofuel. The ignition delay time is function of here inverse temperature for 2 different pressures. I mean, a simulation like this would take, like a minute or half a minute. It's very easy to do this. And then this here shows in a shock tube mole fraction of OH as function of temperature. These were experiments here, I think, were done at Stanford by Ron Hansen. And then here we have flow reactor, like the Princeton flow reactor. Not sure if they showed you this flow, if it even still exists, but they used these flow reactors here for a long time. Mole fraction is function of residence time here for methyl cyclohexane. And then this here shows jet stirred reactor, where you do experiments at different temperatures. And here for endodecane, different species. And then it's very good also to do reaction flux analysis, very simple to do this. This here is for methyl cyclohexane. We don't do these things here automatically, but we're working on the way to get these plots here also automatically, which might be helpful. We talked about laminar burning velocities. This shows laminar burning velocities. Here's function of equivalence ratio. And then, flame structure. This shows the here methyl cyclohexane again for a burner stabilized premixed flame. And you see here, the gradients at the burner here, they are non-zero. And that's why I mentioned earlier, these flames, they sit very close to the burner. And then this shows simulations solving the flamelet equations here for different dissipation rates. And this here is methane air. And so you get different solutions, which then can be used in flamelet tables. So this here is basically a flamelet table where you see you go all the way to, you cover here the entire temperature space. Okay, so this here is a short tutorial. We talk about distribution, installation, code structure, pre-processing, and then maybe a few examples. I try to do this fast. So code, I mentioned this. Here's the link, how you can get the code. It runs on a Unix systems here, a Mac Unix system also, and then also Windows systems. Here's some prerequisites, and then this is how you, there's a README file actually that describes how to do this. This might not be the most recent one, just look always at the README file. It has the most recent instructions, but basically, there's a directory here, and you do this, use this cmake, and then cmake install also, and then code is ready. You can set up the environment so that the paths are set right so that some of the functions are easier to use. It's not necessary, but they're easier to use. And then there's some pre-processing that one could do, which is done by this command here. Right. That's maybe not so important. Now, this is for Windows. I said this to one of you this week. I never touched a Windows computer in my life, so I have no clue how they work. All I know, if you want to turn it off, you have to press the start button, right? Okay, so I don't know how to do this, but there are some instructions here. I mean, again, look in the manual for how to run this, different options how to run this on Windows. Yeah, so this is the structure once it's installed. You know, there's a FlameMaster directory, and it has 4 different or 5 different directories. One is repository. That's where all the source files are. If you make changes to the source code, if you make changes to the source code, that's where you do it. And then that also is the area that would be linked to a Git repository if you do version control. So this is where all the sources are. And then there's a build directory where the make commands are performed. So the source will be copied there, and the compiler runs on these copies. But if you change the copies, next time you do this, it will be overwritten. So make all changes always here in the repository. And then there's here for a directory for binary files that has here all the scripts and also the final codes and all of this. So that's where you find the executables. And then it has a data directory. That's where you find, or that's where you can put, for example, pre-processed chemical mechanisms. The code looks, when you specify use a certain chemical mechanism, the code first looks in the local directory, but if it doesn't find it there, then it would look in this data directory and try to find it there. So you can put all your mechanisms in this directory, and you can access them from everywhere on your machine. And then there's a run directory. That's where you run all these codes. And it has a lot of examples there. There's not a very good documentation of the code, but a lot of examples that one can use. This is the code structure. So there are 4 different parts. Maybe there's a pre-processing in 2 steps. There's the actual simulation, then there's post-processing. Pre-processing is in 2 steps. Let's say you start out. The typical files you have as a chemical mechanism is you have a mechanism file. You have one file that has the thermochemistry data, and then you have one file that has transport data. And so here what we do is, because very often when you work in chemical kinetics, you make a lot of changes in the mechanism file. You don't make much changes in the thermochemistry data file. And so that's why we pre-process the thermochemistry and the transport data files to make it a binary file, and then when you read it, it's much faster. And maybe it's not necessary, but so that's this tool, create bin file, that does that. And then we convert also the mechanism file together with the transport data and the thermo data into a binary file that then has all information, about the chemical mechanism, everything you need. And that's the ScanMan tool that does that. And then once you create a file with this that has all the mechanism data, and then you can run an actual simulation, maybe of a homogeneous reactor and so on. And that's this FlameMaster or FlameMan tool that does that. And then you get some result files, and they can be post-processed. And there's another tool here, it's called list tool, that can be used for that. All of these, they have help functions. So here, FlameMan -H, gives a lot of information about options and so on. I said the main input files are these 3 files here. And then there's also a configuration file that we run here, that we use here for FlameMaster, input file that tells the code, what's the temperature at which I want to compute, what's the mixture, and what's the configuration I want to solve. Do I want to solve a premixed flame or a non-premixed flame? So that's one of the important ones, is here this FlameMaster input file. So this is how this works. Here's the thermo data, transport data, maybe in Chemkin format. And it could now create this binary file. Then the binary file and the mechanism file together can be used here with ScanMan to get this pre-processed mechanism file. And then the pre-processed mechanism file and the FlameMaster input file they can be used to, do any calculation. And then sometimes there are different files. So for example, we want to compute a premixed flame. It's very good to have a premixed flame solution to start from. Maybe if you want to compute a premixed flame, an equivalence ratio of 1.1 is good to have one at 1.0. So that's makes, that's actually is necessary to get a converged solution. Okay, so then here this, maybe I'll go quickly over this. Here this create bin file, the syntax shown here. This would be a typical thermodata file. And so create bin file here used as input thermodata file, transport data file, and the name of the output file name, that's it, okay? So that's can be done here. And by the way, all this pre-processing of all the mechanisms that come with the code, there's one script that runs all of this, if you just want to play around with this a little bit. This was shown here in the beginning. Here, in ScanMan, there's a script that's called create all mechanisms that does all of the stuff that I'm just mentioning. For the mechanisms that are distributed here with the code. And then, so once I have this, I can run ScanMan. ScanMan has its own format that, we defined very early on. So here's allowed atoms, here for example, carbon, hydrogen, oxygen, just defines these. And then some inert species that don't appear in the mechanism can be defined. And so on, and then these are the reactions. Every reaction here has a label. F means it's a forward reaction. Please compute the reverse reaction. If this F is not provided, no reverse reaction will be computed. And then, these are reactions, and then A and E are the Arrhenius parameters. It's kind of obvious, and it's a free format otherwise. And so this is how this works then. ScanMan minus input file minus here minus thermodata file, and then it's the output file, and then here's an example, and then there are a few more options here. This is just for output really, and then so this uses here the GRI mechanism, and this generates then this here this. Where is it? So there's no there's no output file specified. If you don't specify the output file, the name of the output file will be just the input file .pre. Okay, so this is this, and this command just moves this to this data directory I mentioned earlier, and then the code will always find it there. So this is the FlameMaster format, but if you have chemical mechanism in ChemCan format, you can also use these. There's also an interpreter for ChemCan format, and so then we don't use this create bin file. This just shows the syntax, and there's a command here -f ChemCan, and then it uses this ChemCan format. By the way, when this in ScanMan is run, a lot of things are computed already that are used later on, in the simulation to make the simulation more efficient. But also a lot of checks are being done. The stoichiometry of each reaction is checked. The reverse reactions, they can be computed already. And a lot of consistency checks are being done. If you have a reaction appears multiple times, it's flagged somehow. If some mechanisms have negative activation, very large negative activation energies, which makes simulations very stiff, convergence very slow. That's if they are very negative, it's also flagged as just a warning, and so on. Okay, so then we have generated here this pre-processed file that has all the information about the chemistry, and so now we can do the actual simulation. And the actual simulation, I mentioned this, the main input file is this FlameMaster input file. When you run FlameMaster code, and you can specify an input file with -i, and you can call it whatever you want. But if you don't specify an input file, the code looks for a file that's called FlameMaster input. Okay, so you don't need to specify it if you give it this name. Right, and this is how it looks like, and we go through some of these parameters. So here, for example, this is input-output. So, for example, here, if we do homogeneous reactor calculations, we don't do ignition delay, just one ignition delay time. Of these curves I showed you earlier, we compute all of these at the same time, okay? And then at the end, you get a file that has all the ignition delay times. But here, write every solution means also write the time development, time history of species and temperature of each individual solution. And then this is the output path, you know, where you find all the output files. So this is the name of the mechanism file. You specify global reaction. That is useful when you want to specify the equivalence ratio. If you say equivalence ratio is 1, then the code needs to know what the global reaction is that you are underlying this equivalence ratio. And you also need to specify what's the fuel, what's the oxidizer, and then with this information and the equivalence ratio, the initial composition can be determined. I guess that is that. Yeah, in general, commands look like this. I mean, everything that starts with this hash mark is a comment, and then is typically a keyword equal to value or is equal to value. That's the same thing. You know, sometimes is false or true. You know, are options here like this one. Usually, false is the default if nothing is specified. So, and then here the next part is about the configuration. So this says here flame is isochoric homogeneous reactor, or some abbreviation of this, but you could also say isochoric homogeneous reactor, and or isobaric homogeneous reactor, or this could say unstretched premixed flame, or it could say diffusion flame, you know, in physical coordinates, in cellularity coordinates, and things like this. So this specifies, or it could say unsteady spherical flame, you know, things like this. So there are keywords here that allow you to do compute different configurations. This here is an obvious one, phi, that's the equivalence ratio, and you see, or on pressure is pressure, and you see here you can do different, I mean, you can specify multiple values. So if you just specify 3 equivalence ratios, then the code first computes the first one, then the second and the third one. So they're done all at once. And if you specify here 2 pressures, then, you know, it does first 1 pressure, then the second. If I specify 3 equivalence ratios and 2 pressures, all in all, I do 6 calculations. You know, all combinations will be computed. And then this here is interesting for the homogeneous reactor. We specify initial conditions. Here, you know, this, I can specify either X here means the mole fractions. I could say Y is mass fraction. But because here I specify equivalence ratio, this here is not being used. Okay, and then T is the temperature. So what does T equal to 1.7 mean? If I could say T is equal to 1,000, then it would be 1,000 Kelvin, right? That's obvious. But if the value is less than 10, if this value, the temperature is less than 10, it means it's 1,000 over the temperature. Okay, because that's useful sometimes for doing these homogeneous reactor calculations where we want to be equidistant in 1 over temperature and not in temperature itself. So it makes nicer plots. So this means I start out with a temperature of 1,000 over 1,000 over 1.7, and this is 588 Kelvin. Okay, and then you know, solution is being accomplished, and then this continuation here, and then each next simulation always is minus 0.1. So the next simulation will be 1.6, 1.5, and so on. So that, and then the boundary here is 0.7. That's about 1,400 Kelvin. So that would give you all temperature, all ignition delay times for temperatures from 588 to 1,400 Kelvin. And here, continuation type is temperature, and that's it. So this will then, for a given equivalence ratio, first compute all the temperatures, then go to the next pressure here, and again compute all the temperatures. And if you would you know, specify here 3 equivalence ratios, it would do all of this for, it gives you all in all then 6 lines as function of temperature. So you don't need to do much actually to do all these simulations. And right, so maybe I can just show you one example, you know, how we compute this. So let me just oops. Okay, so I go in this FlameMaster directory, and then, oops, no? Premixed, and, oops, sorry, yeah, no, sorry? Size, oh, how do I change the font size here? Sorry? Ah, this was minus, okay. Maybe like this. No, I can't. Yeah. Is better? Good or not? Okay, so let's see where we are. So here in my FlameMaster directory, run, that's where we do all the simulation. And then there's FlameMan and ScanMan. And so here, you know, we're in the stage where we do FlameMaster simulation. And then here we have diffusion, premixed. And so I'm now in premixed. And then I have here 0D, premixed counterflow, perfectly stirred reactor, spherical flame, and unstretched premixed flame. And so here now I go to 0D. Oops. And then I go to maybe n-heptane. And so this is the input file. And now we said we want to do maybe here 3 different equivalence ratios, 2 different pressures, and then the temperatures as we said earlier. And so I just do FlameMaster without the -i because the input file is called flamemaster.input. And then it's just, you know, you see each time, yeah, so that's done. And now there is an output directory and so this here then, this is n-heptane, ignition delay times. Know which one is just ignition? There are different criteria for ignition delay time. So for example here, the CH, maximum of the CH mass fraction, that's what experimentalists sometimes do. And so let's just, oops, copy this. So I use this tool here, it's called Kaleidograph, where now you see I have here my output file. I have, because this is open. So in my output file here, I have the temperature, and then here the second column is 1 over temperature. So you see this goes from 0.7 to 1.7, or 1.7 to 0.7, and then here I have ignition delay times. For the 6 cases, I specified, and I could say now, so I want to plot this as function of 1000 over temperature, and maybe I just show 3 different pressures at stoichiometric equivalence ratio. Oh no, I had 2 different pressures, right? And then always comes up in the wrong. And then here I would say make this a log scale, and then you get these curves, right? And so that's very easy. And I can do now, in addition, I can do, for example, sensitivity analysis, find out what reactions impact a certain species or impact ignition delay time and so on. Yeah, so this explains here the stuff I mentioned earlier. This shows an example. Yeah, this here shows now different example. And here this talks about sensitivity analysis. So this here is the sensitivity analysis for ignition delay times, which shows that, this is a file that comes out, and it shows the sensitivity coefficients. So most important reactions first. Are you surprised? You should not be surprised. The most sensitive reaction, the most important reaction for ignition delay time here of, what was this, hydrogen air, is O2 plus H goes to OH plus O, okay? And what's this, the second most important one, O2 plus H plus M goes to HO2 plus M, okay? And one should be positive and the other should be negative, right? I mean, one should make it fast, the other one should make it slow. And then there are a few more here that, go with HO2 and so on. Okay, and then, so this was homogeneous reactor. Oh, this is reaction path analysis. So here, this here, for example, shows for the H radical, these are the species that produce H, and these are the species that consume. So this positive, negative, and again sorted here by size. And you see immediately this produces H radical, this consumes H radical here. And the main H radical consuming reaction here, of course, again, O2 plus H and also O2 plus H plus M and also O2 plus H. And here for OH radical, O radical, and you can look at the fuel, what consumes the fuel and so on. So this shows perfectly stirred reactor. There's the commands here. Maybe we don't need to go through the details. And then we look at 1D flames. So this was all 0D. If you look at 1D flames, then you have, I think we are out of time again, huh? Then we have, let me just finish this. Maybe we do until 4:30 and then we stop. Then we take the break. 1D flames, then they are stored in a format that's called flamelet file format that was described here in this book. And it's in 3 parts. There's first a header that has a lot of, like meta information, title, mechanism, author, date when it was produced, fuel, pressure, maximum temperature, equivalence ratio, and so on, boundary conditions, and then burning velocity, flame thickness, number of species in the mechanism, grid points that were used, and so that's the metadata here. And then the body then has these vectors, here the spatial coordinate, temperature, a lot of others, and then there's a trailer here at the end which can have some more information that might be case-specific or whatnot. And then, here again, we can just run this. I can specify many different equivalence ratios, and they're all computed at once. I can, I then get these files like this, and this here is something I cannot directly use with a plot program. That's why we use this list tool tool. It takes these flamelet files as input and it gives you a tab-separated column list as output, which then can be plotted also. And then also this list tool program, it can go through the individual files and find, extract this information here. So for example, you can extract the, here the burning velocity and the equivalence ratio, fuel-air equivalence ratio, okay? So then you get a file from all different solutions. You get a file that shows you equivalence ratio and burning velocity, and that allows you then to make a plot like this. So this is this list tool. There's an example here. It shows the symbols you want to extract on this symbol file. This is the output file, and then you see this has the star here. These are all files, all flamelet files in this directory. Yeah, and you can of course also look at species distribution. You can do sensitivity analysis again, reaction flux analysis, and all these things. And then this counterflow diffusion flame, I mentioned this earlier, and here again, maybe we can just see how this is computed. I mean, just also maybe to give you an idea for how long it takes to generate a solution like this. Of course, 1D flames are a little more expensive. So here now I would go to So one more, I guess. And then here I have, no, I'm too far. Back to FlameMaster, and then diffusion flame. And then here I have steady plug flow and unsteady. And so here I just go to steady plug flow. That is the configuration we looked at earlier, where we have two specified nozzles. And yeah, there's an example here. So I just run this example. And you see that's how long it takes. As I said, this uses a Newton solver. Newton solver, I mean, it's a nonlinear problem. It's difficult to converge. So you always need a good start for Newton solver. You always need a good starting point to find the solution. That's sometimes, especially when you have a new fuel, that's a little tricky to do this. But here, typically, you know, we have a solution at one strain rate, and we compute a different strain rate. That's what I did here. Or, for example, you have one fuel, and then the code has an option to say, okay, automatically now replace this fuel by another fuel. Okay, so you slowly, gradually replace one by the other. You do many solutions where you just slowly replace one by the other, and that also helps in converging this. So this now gives a solution, and we can look at the solution. So I convert this with this list tool. So I take this file, convert it, and then it gives me this here. KG means here collider graph. That's the kind of the code I use, but it's just a tab separated file. As I said, you can use MATLAB or something else. So, oops, no, that's not right. This, and now it should just here open this window for me, and now I get here this tab separated file, and I can look at, for example, let's say the temperature, and it looks like this. Well, yeah, now it's the logarithmic scale here, which it shouldn't be. And it looks like this. This is the example I showed. So it looks funny. Why does it look funny? Because on one side, so this is a counterflow flame, but it's not fuel air. There's fuel on one side, and there's a rich premixed flame on the other side. So on that side, you have a rich premixed flame, which is why the temperature shoots up there. And then there's acetylene from the other side. And the idea of this was you have a rich premixed flame, acetylene, you form a lot of soot now. This was a configuration that was made for studying soot formation. It's an old paper a long time ago. This is actually one of the first simulations I did. It's actually my first paper at the Combustion Symposium that shows this. So that's just an example. Now we can also show this as function of mixture fraction, same file, which is this here. And, you know, again, I mean, different things one could do. And then I think we are out of time. Let's see what else is here. Counterflow diffusion flow here for this potential flow boundary condition. And then flamelet equations. You know, we use this for making flamelet libraries. We can, as I said, we can compute this entire S-shaped curve. Also with the unstable solutions, which are shown here. And then this here would be transient flamelets, unsteady flamelets. We use these also sometimes for flamelet libraries, and maybe that's it. So let's take a break now, and let's meet at 4:45.